These are 2 cups of hydrogen clay pebbles. They come from a normal retail 10-liter bag. The only difference is I spent time and selected large size particles to fill the left-hand side cup with, and I spent time selecting small particles to fill the right-hand side cup with. So you can see there's a clear difference in the size of the particles in each cup. So I hope that difference in size is very apparent. So my question is, of these 2 cups, which is going to yield the most empty airspace? Because we know that roots require oxygen. To answer our question, let's construct a real-world scenario and then solve it. So first, let's think of a flower pot. To make it easy on ourselves, let's think of a cubic flower pot. Okay, so let's think of the volume of a cubic flower pot. We know the volume of a cube is length times width times height. So we're going to have our flower pot be 100 centimeters on each side. So 100 centimeters in length times 100 centimeters in width times 100 centimeters in height. Our cubic flower pot will be 1 million cubic centimeters in volume. Now, let's have 2 of the same flower pots, and then let's think back to our hydrogen clay pebbles. Again, to make things easy on ourselves, let's exaggerate things. So remember the big hydrogen clay pebbles? Let's make them huge. So let's take the big hydrogen clay pebble, and then let's say the factory made one that was 100 centimeters in diameter. That's supposed to be represented by, you know, my poor drawing right here. So the cubic flower pot is 100 centimeters on each side. It's supposed to have depth. And then the huge hydrogen clay pebble is supposed to be 100 centimeters in diameter, and so 50 centimeters as the radius. And so if the company made one that big, you could only fit 1 into the cubic flower pot. So we know the volume of the cubic flower pot. Let's think about the volume of the huge hydrogen clay pebble. Well, we know the volume of a sphere is given by the algebraic formula 4 over 3 pi r cubed. So let us sub in of our huge hydrogen pebble. We know the radius is 50 centimeters, so let's put that in as the radius. So 4/3 pi and then 50 centimeters cubed. If you stick all this into a calculator, what you get as the volume of that one huge hydrogen clay ball is 523,598.77, it keeps going, the number, cubic centimeters. So that was scenario 1. Now let's think back to the small pebble. Now the small one is already pretty small. Let's call it a tiny pebble. Each of these tiny pebbles, let's say they're about 1 centimeter in diameter. So each of the tiny pebbles, they're going to be half a centimeter. The radius will be half a centimeter. So thinking back to our volume of a sphere equation, now we put half a centimeter in as the radius. And so the volume of one tiny hydrogen ball is 0.5235987. But again, that is only the volume of one tiny ball. So the huge ball, we could only stick 1 into the cubic flower pot. These tiny balls, they're 1 centimeter in diameter each, so you'd have 100 on each side of the cube. And there's supposed to be depth here. So altogether, you could fit 1 million of the tiny balls. So you need to take the volume of this one ball and multiply it by the number of balls you have, which is 1 million. So that means in the cubic flower pot, when you think of all of the tiny balls together, they make up one total volume of 523,598.77. The number keeps going because pi is irrational, cubic centimeters. So that was the volume of all the tiny hydrogen balls. You see what happened? The volume of that one huge ball was the same as the volume of all of the tiny balls. You see, there's a visual trick going on here. When you have these large particles, you see all of the big empty spaces between them. So you think that, boy, I've got a lot of empty space when I've got these large particles. So in our diagram, you're focusing on that empty space. All of that empty space. You think you have so much empty space. And then, when you have small particles, you don't see as much of those big pockets of empty space. You think you're dealing with a lot less empty space. So, on the diagram, it would look like this. Just tiny amounts, very tiny amounts of empty space. And so you think, gosh, the large particles give me a lot more empty space. But here's where the trick is. What we're forgetting is that each of the large particles is eating up so much empty space. So this huge hydrogen ball ate up all of this space. It ate up all of this space. So here's all of this empty space you are not getting. So you're focusing on this amount of empty space. You're forgetting how much it ate up. However, the small balls, they're just eating small amounts of space. So really, in the end, you have the same amount of space being used by the balls and the same amount of empty space. So if we think back to the original question of which cup has more empty airspace, now we know it was a trick question. Because large size airspaces are paired with large size particles that eat up a lot of space, and then small sized airspaces are paired with small sized particles that don't eat a lot of space. When all is said and done, the net effect is that they both have the same amount of empty space. So particle size doesn't directly affect the amount of empty airspace in a container. I have to say there is an indirect effect through particle size affecting water retention, but I'm not going to talk about that in this video. In this video, I'm just talking about the max empty airspace. So when your medium is dry, how much airspace do you have? Well, if your particles are the same shape, there's no difference. You'll have the same amount of empty airspace. I hope I've made clear that robbing your roots of airspace isn't about choosing large size or small size particles. You get the same amount of empty airspace. It's about combining particle sizes. That way you get the worst of both worlds. You take your large size particle. Your large size particles immediately eat up huge amounts of empty space. Then, where you used to have big air pockets, now you have small size particles. So your small size particles eat up any of those big pockets of empty space. So red signifies empty space. So now you no longer have big pockets of empty space, and then you used to have all of these little pockets of empty space all throughout the middle. But now it's eaten by one giant particle. So it's really the worst of both worlds. So how do you rob your roots of air spaces? You combine large and small particles. And I think I can make it clear with this image here. So, large particles, only small particles, same amount of airspace. Look at this one where I've combined large particles with very, very small particles. Like this is a combination scenario. This one has much less empty airspace. So if you want to rob your roots of airspace, combine your particle sizes. Who would want to do that? Probably nobody, but that's how you would do it.